All right, so in this lesson, we're going to get into the gas laws, and the first one that we want to talk about is what happens to pressure if volume is changing and temperature has to stay the same. Now, if you go to PhET in Google search and you look under gas properties, you can pull up a gas simulation where you have the particles inside and actually do these by keeping certain things constant. Now, if we keep temperature constant, but allow pressure and volume to change, this is what we get. We get Boyle's law, where we look at the inverse relationship here of volume and pressure. So as volume gets bigger, pressure is going to drop, and as it does, it'll look like this. And then this is going to be a constant temperature, and so this is an isotherm. So it's been a little while since we talked about that. That's be an isotherm there. And then our units for volume is meters cubed, and then pressure is a Newton per meter squared, or a Pascal, capital P, lowercase a. Okay, what would happen to volume if temperature is allowed to change but pressure stays constant? And again, you could try this in the gas property simulation, keeping pressure the same but volume and temperature changing. And this is where we get Charles' law. And within Charles' law, we look at how volume is linearly proportional to temperature, keeping pressure constant. And this should kind of make sense. You know, if you have a graph where you're dealing with, volume and temperature, and pressure's got to stay the same. If you're getting a bigger volume, you're going to have a higher temperature to keep the pressure the same. And likewise, with volume and temperatures, you get smaller and smaller volumes. You'd have to get smaller and smaller temperatures to keep the same amount of pressure. Again, volume is going to be in meters cubed, temperature is going to be in Kelvin. And then last here, what would happen if volume is fixed and temperature and pressure are allowed to change? Well, if volume is fixed, you could have a container. Let's say you had a gas container, and I show a video clip of this in class, and you have a container that's fixed volume, and you have gas in here, and temperature is going up, so pressure is going up big time. And pressure is so much that the thing explodes, right? That's where we're dealing with, like a container like this, where the pressure gets too much and actually explodes. And so, this is where we look at Gay-Lussac's law, and pressure and temperature are proportional. So in other words, if we did a reverse of temperature and pressure, and let's say it's cooler this way, if we get cooler and cooler, pressure is going to drop, right? And so pressure is going to get less and less as we get cooler and cooler. And we can work our way all the way down to the x-axis, where on the x-axis we should get to absolute zero, because that's where theoretically pressure would be zero. And we know it's not, with the quantum state there, but yeah, that gives you a good picture there. Now, this is a really critical slide here. What's the difference between internal energy and temperature? Remember, internal energy is the total amount of energy the particles have in a substance, plus a total kinetic and total potential, both. But temperature is just measuring the molecule's average kinetic energy, just looking at averages. So the example I like to use is, like a cup of hot chocolate, where, inside there, you have a higher temperature, but low internal energy as compared to an igloo. An igloo has many, many more particles. Even though they're moving slower, this igloo has a higher internal energy but lower temperature. Very important to distinguish those two. So if we look at this apparatus, we have, this is James Joule's apparatus here, where we have a mass that's hanging, and what he was able to do is look at the potential energy here that turns into kinetic energy of the paddles, that heats up the water, and get the mechanical equivalent of heat. And that was a really critical thing that he was able to do. So what happens is, when we look at non-conservative work is caused by friction, force of friction, and therefore, it's going to be taking away from the energy of the system. We can bring it over, and this becomes part of this this full equation here. And looking at non-conservative work in relation with the change in internal energy, very critical here. So let's go ahead and try this problem here, L3. We've got a bullet that's passing through a block, and the bullet is 25 grams, which is 0.025 kilograms. It goes through the block going at 255, slows to 25, and ignoring the small change in gravitational potential energy, go ahead and determine the internal energy of the block and bullet after the impact. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so the initial speed is 255, the final is 25, and we have the conservation of energy here, which we can find the change in internal energy, which will come out to be 805 joules. And so that's going to be given to the block and bullet. If we touched it, they would be warmer because of that internal energy that would go into it and make it a higher temperature. All right, so let's say that we have a jet that's landing, and it's going to come to a stop. The landing speed's 57 meters per second. Takes 1,829 meters to stop. This will be good review for us. Go ahead and calculate the non-conservative work and the force of friction for bringing this aircraft to a stop. And this is the overall, non-conservative work and friction due to braking and spoilers and any other factors there. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so yeah, non-conservative work. There's no change in gravitational energy. There's no springs involved, no rotational energy that we got to consider. So 390 million, no, 39 million joules or Newton meters is non-conservative work. We can solve for the force. It should take 21,352.98 newtons. And then the final question is, what is the increase in internal energy? And so the big thing here, and this was another really key slide, was the fact that the increase in internal energy is the non-conservative work. Those brakes and the air and the whole surface is going to increase by this many joules of internal energy due to the non-conservative work, because all that energy went into thermal energy, which comes out in the form of non-conservative work.